Hey, we got a new star. Her name's Ray. You want to look at the camera, Ray? Here, look. The puff. Look! Smacked my hand. She wants to get the puff herself. So you can see the puff is on the table. Sometimes she puts them into her mouth. Most of the time she makes it. So, let's see. Hey! She's an expert. So hopefully that's a little, oh, there you go. A little encouragement from the Repulse clan to keep on going with what you have to do. So I'm going to put her away because if she stays here, you guys are never going to pay attention to me, so. Alright, nuclear reactions. Let's get down to business. 3 types: alpha, beta, and gamma emission. Or your textbook calls it alpha, beta, and gamma decay. Same thing. Alpha decay is when you lose 2 protons and 2 neutrons. 2 protons, 2 neutrons. That sounds a whole lot like helium. Helium has 2 protons. Well, it is. Alpha decay is especially common when something is large. And so you have uranium, and it loses 2 protons, so it goes from 92 to 90, and 2 neutrons, it goes from 238 to 234. Well, that doesn't look like 2, that looks like 4. Well, exactly, because the mass number, or the nucleon number as it is currently called, is protons and neutrons combined, which makes, in this case, a grand total of 4 particles, and creates a lot of energy. Alpha emission. Beta emission is where you have a neutron become a proton. What in the world? Sounds strange, but it does happen. And so it also allows us, because it creates an electron. Now, to be honest, I don't fully understand how this all happens. It has to do with quarks and how the quarks are reshuffled. And a lot of math that goes on here, a lot of really small math, and a lot of calculus. And so I'm not going to go into that, but all you need to know is a neutron actually becomes a proton. So you got this thing here, iodine, which is really large, but has a small number of protons. It's like, yeah, I'll just make a neutron into a proton. So its mass number doesn't change, or its nucleon number, but its number of protons does. It essentially gets taller in our illustration. And so its mass actually doesn't change, but it actually changes what it is to become larger. So, lastly, gamma emission is the emission of what is called a gamma particle. You see, gamma is this little Y here. It's a gamma photon. And usually happens after alpha and beta emission have taken place. You see, even if you do lose energy, or let me rephrase that. If you lose particles, you still have the same energy that you had before, and of course larger atoms have more energy. And so it's almost like a release of powerful energy. Gamma radiation, gamma emission, gamma decay is the strongest type of radiation. Unlike chemical reactions, the rates of nuclear reactions are unaffected by temperature, pressure, presence of other atoms, etc. Everything that you'd expect from a normal chemical reaction, it's not affected by. Whole year we've been talking about how atoms affect each other. Okay, what does chlorine do in the presence of sodium? Yeah, they combine ionically. Doesn't happen. You can throw sodium in there, it does nothing. That's because nuclear reactions just deal with the nucleus. However, nuclear reactions give off a lot more energy than a chemical reaction. Now, Oh, there's my mother. Oh boy. Anyways, I'm gonna head outside and keep recording. Well, anyway, it was raining, so I guess no outside for me. Half-life. And, it's the time it takes for one half of something to disappear. Something radioactive. Now, let's use a strange illustration. Okay. To make a chart of how this might work. I'm going to give this illustration. Let's say caffeine has, let's find out. Half-life of caffeine. 5 hours. Alright. Has a half-life of 5 hours. Now, the half-life is the time it takes for half of something to go away. Particularly something radioactive. I'm not saying caffeine's radioactive. But caffeine chemically disintegrates after 5 hours. So you can make a chart. And so let's have this be half-lives. Let's have this be time. And this be amount remaining. So if at 0 half-lives and 0 time you consume 100 milligrams of caffeine. Oops. After 1 half-life, which is 5 hours, you would expect half of the caffeine to go away. Thus, you have only 50 milligrams remaining. That's why after you drink caffeine, you know, it's not really present after you go throughout your day. Your cup of coffee might last you throughout the morning and afternoon, but by the time the evening rolls around, 10 hours later, you only have 25 milligrams of that caffeine remaining. And by the time the night rolls around, that caffeine, there's very, very little remaining. Not enough to keep you awake, and so you can head to sleep only to drink more caffeine tomorrow. So that's how half-lives work. And you can see here, after 1 half-life, 50% of it's remaining. 2 half-lives, 25%, 3, 4. Now you have only a fraction of what you originally had. That's how to do a half-life chart. It's actually not very complicated. If you need another example of that, you can just Google it, as we are learning from the internet. Now, radiation's effect on the body. Radiation changes things, leads to harmful free radicals. And these are particles with unpaired electrons. Consider water. You get water, you allow some sort of radioactive emission to come in contact with it, and it can become some pretty strange things. So it can become a charged water particle with an electron. It can become hydronium, or H3O, something very acidic, or hydroxide, something very basic, or a hydrogen that doesn't have any charge, or a hydroxide that doesn't have any charge. Those things are not good, because if they get in your body, they actually steal your charge. They say, hey, you don't need that charge, I need that charge. And since they're very strong, they actually can rip those charges off of the things in your body that need the charge. Calcium gates in your blood vessels or something, they'll rip the charge away from the calcium, because hydroxide is much stronger than the calcium is. And these can react with the body, causing things like cancer. Now, it's not to say all nuclear radiation, radioactive nuclides is bad. You can use them in cancer treatment, computer imaging, smoke detectors, food irradiation, etc. So they do have their uses in society. Now, we're going to go over the logistics of the nuclear reactor in chapter 17.5. But in a very basic way. You can see this diagram here, and you can see how, here's my thing. Here's the containment structure. The containment structure holds the reaction. This reaction is happening. The core of the control rods make sure they can control what's going on. Produces heat, which makes steam. The steam turns a turbine, and the turbine runs an electric generator. So when you pass a giant nuclear reactor and you see all the things coming from the top of it, and you're like, whoa, they're polluting our environment. It's just water, just steam. So nothing too harmful there, even though we might be afraid of it. A becquerel measures nuclear disintegrations in a second. And sometimes an older unit is like a Curie, named after Marie Curie, a very famous female scientist, is used, depending on, of course, the institution you're in. And those measure the speed at which a nuclear reaction is happening, the amount of nuclear disintegration per second. Just a couple more things here before we end 17.3. There's different types of nuclear reactions. There's bombardment reactions, where a nuclear reaction is induced by pelting a sample with other particles. Particle accelerator, also used in many things in physics, uses electric fields to initiate nuclear reactions. So you can see, bombardment reaction, you have a fast-moving alpha particle, or helium. It bombards into something, and all of a sudden a new element is created. It sounds a whole lot like medieval alchemy, where they were trying to stir lead and make gold. We can actually manufacture gold if we want. We can just make it. Unfortunately, bombardment reactions are very expensive to occur. So it's not like we can just make whatever metal we want just by shooting it with helium. Technically, we can. Technically, it costs a lot of money. A lot more money than just the natural mineral's worth. But we have done this. Fast-moving particle creates a completely new atom, whereas a slow-moving particle would just bounce off. The helium would just bounce off and keep being helium. This is a Large Hadron Collider. That's the world's largest particle accelerator. It uses electric fields to spin electrons, and this actually creates a loop. It's like a tunnel. I think it's somewhere in Holland. If I'm not mistaken, it could be in Finland or something. But it's a European country, and they do experiments on physics and how to make better electronics with this particle accelerator. And lastly, transuranium element is one beyond uranium, artificially prepared by bombardment reactions. So if you see everything past uranium, neptunium, unium, whatever, ununium is 118, I believe, protons. And all these have been artificially manufactured. None of them actually exist in nature. It's prepared by a bombardment reaction where we're just slamming it with neutrons, making it go through beta decay to become something higher. And typically these things that we make don't last very long. For instance, NP, I believe, is neptunium. It's not very stable. It's not like you could hold it in your hand and play with it, like Play-Doh. Neptunium is very unstable. It goes through radioactive decay very quickly. Some of these last not even a fraction of a second before they have a nuclear meltdown and become something simpler. And that's all. And that concludes 17.3. Make sure you do your section reviews on page 300 and get those back to me. I think this is the last assignment for this week. So congrats on making it this far. Hopefully you can join me next week for 17.4 effects of radiation on matter. Alright, see ya.